All right, so today's discussion is going to be on nuclear magnetic resonance, also known as NMR. And so NMR uses, it's also, I guess, NMR spectroscopy, and that's because it uses radio waves, part of the electromagnetic spectrum. And so radio waves are going to be low energy, and so, one of the interesting things about nuclear magnetic resonance is that um, the same technology is used in the organic chemistry lab as it is for MRI, except I believe we really just take away the nuclear portion for the magnetic resonance imaging. We take away nuclear because nuclear kind of sounds scary, right? Like a nuclear explosion. And so although they are the same, we call magnetic resonance imaging for medical purposes, and then in the organic chemistry lab, for example, we call it nuclear magnetic resonance. And so, really, what we're doing is we're taking a look at different nuclei. Okay, so nuclei, and really the two common ones that we're going to see in our level of organic chemistry is the proton NMR as well as the carbon NMR, but specifically carbon 13. Okay, and so this is also called the proton NMR, and then this one is just called carbon NMR. And basically, what the proton NMR can do is it will determine the number and type of hydrogen atoms in a molecule. So number and type of H's. And then this one will give you the number and type of carbons. And so what do we mean by that? Well, it's really just like kind of classifying as if you have like a primary, secondary, tertiary, and we can even get more in depth and kind of tell you what they're next to. For example, is there a tertiary carbon next to a secondary or primary carbon, and things like that. So nuclear magnetic resonance is really useful for determining the chemical structure of unknown compounds. And so I would say this is the most important thing. Oops. So determine structure of unknown compounds. NMR is an amazing tool, and it's so fun to use. It's kind of like, I don't know, if you like Sudoku or you like puzzles or whatever, this is like the kind of chemistry version of that. It's just, I don't know, it's a lot of fun actually. It takes a lot of practice to get really good at it, but once you do, you're having a great time solving these. And so, how does NMR spectroscopy work? Okay, so how does NMR spectroscopy work? Well, nuclei of a given atom, they actually have spin in a similar manner to electrons and how they have spin. Okay, so nuclei have spin. So remember, these guys are positively charged, and these positively charged nuclei therefore interact with an external magnetic field. Okay? And so let's just say we had a set of atoms, and we have as they're just kind of floating around, let's just say in a beaker or whatever, they have randomized spin, or basically a random magnetic field orientation. And so this is actually really hard for me to draw random directions. But let's just say those arrows represent the direction of that magnetic field. And so once we apply that magnetic field, so let's see if I could draw a pretty arrow for you guys. Okay, so this would be our applied magnetic field, and this would be indicated by B naught, or B with a little subscript 0. And let's say we still have those same nuclei, and now, however, we've got a population of those nuclei having a spin in the same direction as the applied magnetic field, and then we also have a population of those nuclei in the opposite direction. Either way, these in the presence of the strong magnetic field, the nuclei adopt a specific orientation, right? Specific orientation. Now let's take a look at basically the orientation of these nuclei. So imagine we have, I kind of like the way I drew this, so I'm going to copy this real quick. Copy that. And then we'll bring it down here, paste that. So imagine we have an applied magnetic field. So oriented nuclei can absorb energy, causing something called a spin flip. But really, what are we looking at? We have one state for that nuclei, where this would be kind of one of these guys up here, right? With the orientation being pointed in the same direction as the applied magnetic field. So in this case, it'd be kind of like the red one. But we also have so this is the low energy state, sorry. So low energy state. And when your nuclei absorb energy, they can cause a nuclear spin flip. And what that results in is the spin being pointed downward. And so this would definitely be the higher energy state. And whoa, what was that? Are those even letters, guys? Are these even letters? Higher energy state. Okay, and so this would be the alpha state, and this would be the beta state. Now, what we're looking at right here is essentially an energy difference, right? Now, that energy difference is actually an important, I guess, an important idea to kind of pay attention to. So, energy does interact with the molecule, but absorption occurs when the incident energy matches the energy difference between the two states. So, it has to be basically equal to this energy value. And that energy value is essentially the amount of energy it requires to have this nuclei spin and be pointed opposite or opposing that applied magnetic field. Now, it's just, just think of it as like the low energy state is, yeah, you just go along with things, right? But it takes a lot more energy to go against the flow of things. And so that's where you can kind of think of this blue arrow being pointed downward being higher in energy, because it's opposing that magnetic field, and that's good. It takes energy, right? And so when the oriented nuclei absorb energy causing that spin flip, that's something called resonance. Okay, so I'll put resonance. It is in resonance because it was the frequency of the incident radio waves, for example, are equal to the amount of energy that is required to cause that spin flip. So basically the frequencies of those energies match up, and they are in resonance. And so basically this delta E is equal to h nu is our relationship with energy and frequency, right? And so the frequency that causes resonance depends on three factors. So we have the strength of the external magnetic field. Whoa. So I wanted to put B naught. We also have the electronic environment of the nucleus. Electronic environment of the nucleus. So basically, whoops, I'm not being consistent with that. And then we also have the identity of the nucleus as well. So ID of nucleus. Okay, so the strength of the magnetic field, first of all, usually we're talking about frequency of the energy that causes the resonance. That frequency is discussed in terms of megahertz. So we'll do megahertz. Okay, and this is measured in Tesla. That's the units. And basically, the stronger the magnet, the stronger the radio frequency required. Okay, stronger B naught equals stronger radio frequency required. Okay, and we'll discuss this further in just a minute, but the electronic environment of the nucleus, that's basically, if you think about all of the nuclei, if they're spinning charges, right, they're their own tiny magnets. And so if these guys are their own tiny magnets, they're creating their own magnetic field. And we're talking about how magnetic fields affect the spin of these nuclei, right? And so if they're surrounded by a lot of, well, basically, in short, they are affected by the magnetic fields of the adjacent nuclei. And so structurally, every organic molecule is going to be different. And so every organic molecule is going to have a unique magnetic environment for each of those nuclei. And so that's why NMR is so useful, because we will have a very unique NMR spectrum for each molecule. And so some of the factors that can affect the environment of that nucleus would be things like the electronegativity, so electronegativity of atoms around it, atoms surrounding the proton or carbon in this case, as well as resonance structures. And then also, it could be like in three-dimensional space. So there's a lot of other reasons that we could affect, or other ways that we can affect the magnetic environment of specific nuclei. And so, again, this is why they're all going to be different and have different absorptions of energy, and therefore different NMR spectrum. Okay, so the identity of the nucleus is the last factor that the frequency depends on. And so some NMR, or some nuclei are actually not even NMR active. So I'm going to write this one in red because this is important. Some nuclei are not NMR active. Okay, and again, this just depends on the number of protons and neutrons, and so you must have an odd number of protons and neutrons to have a nuclear spin. Okay, so must have odd number of protons and neutrons. Sorry, or. Okay, and that's exactly why we use carbon-13 as opposed to carbon-12, because carbon-12 it has an even number of protons and neutrons, and is not NMR active. Okay. And so that's why we're looking at carbon-13, which does make it a little bit more difficult because, as you know, carbon-13's abundance is really, really small. And so, yeah, that just makes it quite difficult. But technology is amazing now, and so we've got our ways. Now here's an image of an actual NMR spectrometer. Now this is just kind of a basic example of what we might be looking at in a laboratory. So this, as you can see, we have a desk right here. So that gives you a relative idea as to how large this one is. Now this is actually pretty small. This is probably what we would call like a 300 megahertz instrument. So I could walk up to it and then stand there and place this. I would have to reach, but I could place my sample inside the top, where that red arrow is. Whereas some NMR spectrometers will actually be the size of like a one-story. Well, basically, you got to get on stairs to go up. You got to go upstairs to kind of place your sample inside, or you got to get on a ladder. And so those are the much bigger magnetic. Those ones are the ones that have the larger magnets. And so, for example, 900 megahertz, you got to get on a pretty decent ladder. I'm only mentioning these specifically because I've used these ones. We also have a 60 megahertz in our lab, and this is pretty much the size of that computer screen. It's even smaller than a computer screen. It's just, but it takes about the same space on a benchtop, and so 60 megahertz to 300, it's quite a big difference, but they both function the same way. Just the larger the instrument, the better resolution. Okay, so better resolution, meaning you're going to get better splitting in between your peaks. If you have peaks that are close in energy, so close in frequency, they're going to be very close together. But if you have a higher strength NMR, then you will get better separation. All right, so let's take a look over here. We've got our magnetic field and its dependence on the radio frequency, or the radio frequency's dependence on the strength of the magnetic field. So let me draw you another diagram. It's going to be similar to this one here, but slightly different axes. So here we'll have energy. And then on the x-axis, what we'll have is an increasing magnetic field. Okay. Now let's say we have, well, let's go here, here. Now we've got two nuclei here. We got boom, boom. All right. Now as we kind of increase that magnetic field, these kind of angled arrows represent the relative energy differences. And so, for example, here, let's say we've got this lower energy state with this higher energy state. Okay, that's one energy level. And then as we increase the magnetic field a little bit more, coming down here, we can get another energy state. Okay, and so what we have here is increasing magnetic field, or let me just do B naught. B naught means increase in energy required to do the spin flip. Required for spin flip. Okay. Now, the reason why we bring this up is because I want to talk about something called shielding. Okay, so shielding is a really important topic or vocabulary word related to NMR spectroscopy as well as our NMR spectra. So when we have our nuclei, they also have electrons surrounding them, right? And so basically what shielding is those electrons surrounding the nuclei counteract the effects of the external magnetic field. So equals electrons, they create an opposing magnetic field. Okay, and so this reduces basically the amount of, or the strength of that magnetic field that the nucleus feels. Reduces the strength of the magnetic field felt by the nucleus. Okay, and so if it reduces the strength of that magnetic field that it feels, then it's basically, if it were going to be here without those electrons, now it's going to be here, which means that it's going to require less energy, right? And so this is going to occur throughout every single molecule because everything has protons and electrons, and so, but every environment is going to be different and very unique, and so that's why again we get a variety, or everything has kind of its own unique magnetic or nuclear magnetic resonance spectrum. Okay, so basically what we have is the idea of B effective. So the effective magnetic field is equal to the B applied, the magnetic field applied, minus the magnetic field of the local environment. So differences in the electronic environment lead to different intensities of shielding. Okay, differences in magnetic environment, or I guess electronic environment, as creates a different magnetic environment. Environment create different magnetic environment. And therefore different intensities of shielding. Different intensities okay, so that means that some are going to be strongly shielded and some are going to be weakly shielded. So here we go. Really what we're saying is if we have an applied, oh wait, where's that? Did I copy that? Ooh, still got that gorgeous applied magnetic field right here. Let me make that smaller. Okay. What we want to do is we have this guy, we have our nucleus, and then we've got some electrons kind of flowing around it. Oh, that's bad. Okay. I should draw this better. I'm going to draw this better, y'all. Let's draw a big one. And I didn't want to do that in black. The worst. Or I didn't want to do that in red. So I'm going to change that to black. I'm sorry. Y'all are having fun, right? Okay, so what we're looking at is that's a little bit better, right? It's like, it's not that bad. It's like Saturn's rings, and we have the applied magnetic field here, and then since these electrons are kind of rotating around, what we're going to get is a magnetic field pointing in the opposite direction, depending on obviously the direction that those electrons are flowing, but they will be opposing, and in this case, and then we will get that decrease in the strength of the magnetic field because you have the B applied, meaning here, and then minus B local, which is, this is B local, and therefore we have a B effective, and so that is the shielding that we are observing. And so the nucleus is shielded. Okay, and this requires less energy for spin flip. Okay, and so what that's going to look like is pretty much we're going to require us to introduce what an NMR spectrum looks like. Okay. All right, so this is pretty much what our the x-axis is going to look like on our NMR spectrum, and the x-axis does represent the chemical shift, which we'll discuss in a minute. And then the axis is numbered from, actually on the left side is 14 and on the right side is 0. So it's almost counting down, right? Now, as we go from right to left, what we're going to see is that we have an increase in de-shielding. Okay, and then obviously what that means is as we go from left to right is we have an increase in shielding. So what that means is on this side, what we're going to have on the right side is more electron density, right? Because if there's more electron density on that substance or that nucleus, around the nucleus that we're observing, then it's going to cause more shielding because we have more of a kind of an opposing magnetic field created by this electron density. So, and this would have less electron density. This is going to be helpful in kind of predicting where chemical shifts are going to be. If you have heteroatoms, then it's going to obviously be de-shielded because they're withdrawing electron density from the nuclei of interest. Okay, and so pretty much what we would be looking at is if we had just a proton, for example, what would happen is we would get like a peak in the NMR. That's kind of terrible, but if this would be the proton, and then if we had the proton plus the electron, so this would be proton plus the electron, then we would get that shift in the and to the right, and this is actually called upfield. Okay, and then if we were going to go in the opposite direction, so going from right to left, this would be shifting downfield. Okay, and so this would obviously be when we have a little bit less electron density, so we have more electronegative groups around the nucleus, and so we feel more of that applied magnetic field. And so this will make more sense as we kind of do more and more examples, but let's take a look at that chemical shift and what that really means. So chemical shift, and it's basically the position in which the nucleus absorbs. So that would represent the energy, right? Because remember, the energy is related to the frequency associated with that spin flip. And so you can think of if you had a nucleus, got that opposing magnetic field, and this is the high energy state. and then we have this low energy state. Oops. Essentially what happens is this guy relaxes, so it goes woo, and then all of a sudden we end up in that low energy state eventually, right? So when we're applying the magnetic field and the radio frequency, we are only doing it temporarily. So we're going to excite that nucleus essentially and cause that spin flip to occur, and then eventually it's going to relax. And when it relax, and then go down to that lower energy state. And when it does relax, it releases that radio frequency, okay, the RF, and that's pretty much what we're observing with our instrumentation. And when we observe that, it gives a very specific chemical shift, essentially. And so the delta scale is used for NMR. So delta scale, and that is represented by this guy. And 1 delta is equal to 1 part per million. And so that's why we had ppm on the bottom for this chemical shift. And that's because if we were working with hertz, then those numbers would be really large. But since we've converted to the delta scale, which is the observed chemical shift, for observed chemical shift divided by the spectrometer frequency, so spectrometer frequency in megahertz, then we get a much nicer scale, again ranging from 0 to 14 or 14 to 0. And so it also makes the spectra universal, and so that way when we are using like the 60 megahertz instrument in our lab, the same chemical shift basically the proton chemical shifts will show up in the same region as they would for somebody else in like a fancy national lab, for example, using like a 900 megahertz instrument. And so it kind of normalizes it to make all the chemical shifts the same and easy for communication purposes. So delta scale essentially makes the spectra universal and applies to all magnetic fields. Spectra universal and applies to all magnetic fields. Okay, so let's take a look at NMR spectrum or NMR spectra and look at their common chemical shifts. So here, I'll put this guy right here. Here's an example of some kind of just approximations for chemical shifts. And so we have that scale of 0, on here it's 0 to 12, but typically you might see the window from 0 to 12 or 0 to 14. It's the same thing. And what this is showing you is that the hydrogen highlighted in red in all of these is going to show up in this particular region. So for example, a carbon with the hydrogen on it, also known as like an sp3, an sp3 carbon that is completely saturated, absorbs at higher fields. So remember, this was called upfield, and so this is also going to, the way we might discuss this proton is we would say that it would absorb at higher fields. Okay, and so the protons on the sp2 hybridized carbons absorb at a little bit lower fields, and then the protons bonded to electronegative atoms absorb at even lower fields. And so you can see that, well, we've got our heteroatoms here, and then I think I said even lower field. Sorry, the alkenes and the heteroatoms are kind of, even though they're explicitly kind of drawn side by side on here, they can kind of go switch back and forth. So it kind of just depends again on the magnetic environment of the organic species that you're discussing or observing. And so, but these are nice little tools to kind of, or this is like a nice kind of generic outline of what we would expect, right? We have the things with more electron density on the right, and then, for example, that proton on that carboxylic acid it's kind of, I mean, it's an acid, right? So it's viewed as like an H plus, meaning it doesn't really have much electron density on it, and so it's going to be really far downfield and highly de-shielded. Okay, and now an even better example of the chemical shifts would be something in this chart. So let's move that up here. So it's just kind of, let me make it a little bit bigger. All right, so really what we're looking at is we have an sp3 hybridized carbon with a hydrogen on it. So we can have 3 hydrogens, 2, or 1, meaning we have either a primary, secondary, or tertiary carbon, and as you can see, we have the chemical shift moving down, and so that's just going to be something that you're going to have to note. As you can see also that they are pretty close if we're considering the whole spectral range, meaning 0 to 12, basically 1 to 1.7 is not much of a difference, and so yeah, I mean, basically what we're looking at is 0.9 to 2 for the hydrocarbon hydrogens, right? And so you can see we can have things like this where we have heteroatom Z on doubly bound to another carbon, and pretty much the alpha hydrogen. Remember, this is on the alpha carbon. If it were like a carbonyl or nitrogen, we got the alpha carbon there, so we would have like an alpha hydrogen is going to be 1.5 to 2.5. And we've got our alkyne hydrogen at 2.5 about, and then we've got our carbons directly bound to a heteroatom and also directly bound to the proton in question. Those are going to be drastically affected by the electronegativity of Z in this case, and so those are going to be more downfield. And then as we kind of progress, we've got boom, boom, we've got the alkene, we've got the aromatic hydrogens. Those are like way over 6.5 to 8. That's crazy. The aldehydes, we've got this kind of that electronegative atom, oxygen, kind of withdrawing electron density from that hydrogen. And there's a few things in addition to just the electronegativity of these atoms that are affecting the location of these resonances. And we'll discuss that in a second, but for now, this is pretty much what we're looking at. And so we have ROH and the NH, so alcohols and amines, those range from 1 to 5. These guys move around a lot. Even if you run an NMR of the same sample 2 times, maybe even with different solvent, you're going to get a pretty different chemical shift because they do hydrogen bond. And so depending on the concentration or maybe the amount of water in your sample, that can affect the range drastically. And these are going to look pretty broad as well. And so what I mean by broad is, as opposed to like a sharp peak like that, they might just show up as a little blip on the NMR spectrum. And so again, we'll get some practice in and we'll kind of see what I'm talking about when we do this, okay?